All right, the final topic for our 2D trusses, finding the forces in statically determinate 2D trusses, is using the method of sections. You can use the method of joints, the method of sections, you can use them together, you can use only one, whichever one you find the easiest to do is the right one to use. So what is the method of sections? Previously in the method of joints, we we solved for equilibrium at each individual joint. Now we're going to break up our truss into a section, which will have multiple joints, multiple members. So we're going to determine the reaction forces in the individual members by passing an imaginary line through the truss, cutting it up into two different sections, and solving for equilibrium for each section. So what equations of equilibrium can I use for the method of section? I actually get to bump up to 3. I can do the sum of the forces in the x direction. Again, this is a 2D truss, so we only have 2 forces. Sum of the forces in the x, sum of the forces in the y. I also get to solve for the moments, right? That's because previously, right, so this is 3 equations. Previously, I only had 2 for the method of joints. So a joint is a pin joint and can only transfer forces. It has no moment. So I only had 2 equations that I could work with because I was kind of looking at a joint on its own, like a point. Now if I'm looking at a larger section, I can solve for global moment, right? I'll still not be allowed to have a moment transferred at my pinned connection, but my entire structure has to have the sum of the moments equal to 0, or my entire section, if that makes sense. So some of the forces in the x direction is equal to 0. Some of the forces in the y direction is equal to 0. And some of the moments around z is equal to 0. I get to use the same two approaches for assuming tension or compression. I can assume that all of my members are in tension, and then if they come out negative, then they're in compression, or I can make a guess, and if my sign changes, then apparently my guess was wrong. So, okay. So what does my method of sections look like? Let's say I take this truss and I break it up into 2 different sections. If I look at my truss as a whole, I have a reaction at D in the x direction and a reaction at D in the y direction and a reaction at E in the x direction. Now if I break it up, I still have those reactions. D in the x and y, and E in the x. But I have to assume the forces in my members. So my force in member BC, assuming it's in tension. My force in member GC, or CG. Right, equal and opposite, because where I cut it. And my force in member FG. Now I probably could have solved for those reactions just as the entire structure if you want to, but that wouldn't give me my member forces. So if I look at section on the right, I'll call that section number 1. It has one known. It has the applied force P. It has one known force. And 1, 2, 3 unknown forces. Now, since I can have 3 equations of equilibrium, I can solve this. Right? I have 3 equations and 3 unknowns. My 3 equations are the sum of the forces in the x, sum of the forces in the y, and sum of the moments about z is equal to 0. I have 3 equations and I have 3 unknowns, so I can solve this. So section 1 is super easy to solve for my member forces. If I go look at section 2, use purple, the section on the right, I have 0 known forces, and I have 1, 2, 3, 4, 5, 6 unknown forces. So I can't solve using equilibrium. Now what I could do, if you're thinking about, oh, what would my strategy be? Well, I could solve section 1, and then I know those 3 member forces, and they would transfer over to section 2. So then I only have the 3 unknowns being my reactions. And there you go. I have 3 unknowns. You could solve for the entire thing, solve for the reactions, and then solve for the individual section number 2, because you have the 3 reactions as known. You know, however you get to the end, I can't tell you exactly everything to do. You can go about it a number of ways, but these are different approaches that you can take. So this is a visual representation of the method of sections. What does the method of sections look like written out procedurally? I love a good procedure, right? Procedural. I watch Law and Order way too much. So I like a good procedure. What's a good procedure for method of sections? If necessary, you can solve for equilibrium of the entire truss to determine your support reactions. You could also, in here, check out and see if there's any zero force members, because that's super easy to just knock those off. Choose a location. All right, I'll just ask that. All right. Choose a location that you want to cut to create your sections. Now, the method of sections is especially useful for creating or for determining member forces a little bit more efficiently than the method of joints. Maybe you could figure out your support reactions globally, but then locally, if you need to know all the members of the member forces, you can use the method of sections. So I'm going to choose a location to cut, and I'm going to draw a free body diagram of a section. With at least one known force and at most 3 unknown forces, right? I get to bump it up to 3 because I have that extra equilibrium equation from the moment. With joints, I could only have at most 2 unknown forces, but now I can have 3. You get to choose your approach for determining tension or compression. Then solve for equilibrium at your section. If you have any concurrent forces, take the moment about that point so that you can eliminate them when you're taking some of your moments. Right? You know, if you have got a pin, so you have a vertical and a horizontal component to your reaction, take the moment about that so that you eliminate two unknowns, and you could probably just have one unknown. Well, you should, because you only supposed to have three. So, yeah. So draw a free body diagram of your section. It can only have one known force and at most three unknown. It has to have at least one known force and can only have at most three unknown forces, because we only have three equations of equilibrium. Solve for equilibrium of your section. That's a little tip right there for taking the moment about things, so you don't to make it easier on yourself. And then continue through your entire structure, ensuring equilibrium of each section and your entire structure. Right, just as you did the just as you did with the method of joints, you work your way through the structure. You can make different sections if you want. So let's work through an example. Oh, continued. I thought I was going to write bigger. I didn't. That's why I ran out of space. La, 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 la. Okay, here's an example for using the method of sections, right? Let's see. Are there any zero member forces? I don't think so. Or zero force members? Actually, I see one. Right? Oh gosh. How about X is the horizontal and Y is the vertical? Well, I'm going to have a zero force member of DE, right? I take the sum of the forces in the Y direction at E. But that doesn't mean that CD or DF are going to be 0. AB and AG would be 0, except there's that point load of 1,000 newtons right there. I think that's the only one I can assume is 0. So let's draw our little section right here. All right. Gonna go on to the next page. Gonna look at this section first. I have force in member BC, a force and member, right? I have C like way out here. And the one right here is F. So force in BC, force in CG, and a force in FG. Let's see. The easiest place to start would probably be some of the moments about, actually some of the forces in the y direction, right? Because the only member with a vertical component is FCG. So let's see. Some of the forces in the y direction is 0. I have negative 1,000 newtons as my point load, plus the y component of the forced member CG. Now, if I go back and look, this is 2 meters by 2 meters, so this is a 45-degree angle. So my vertical component of FCG is 1,000 newtons. Right? It is in tension. And let's see if this is 45 degrees. FCGY is FCG times the sine of 45 degrees. So FCG is 1,000 newtons divided by Alright, so FCG is FCGY divided by sine 45. That's 1,000 newtons divided by sine of 45 degrees. Get out your calculators. Make sure you're in degrees. 14 newtons, right? So let's see. I could take the forces in the x direction, but I have two unknowns, FBC and FFG. Instead, I'm going to take the moments about G. Why am I taking the moments about G? Because if I take the moments about G, I don't have to account for this moment or this moment because they meet right here. Right? If I was going to draw that, it's really like I have that force and that force, and they're acting right here. So I can eliminate taking them to account. So some of the moments about G, counterclockwise is positive. FCG and FFG don't count. So I have 1,000 newtons. This is 2 meters times 2 meters minus, right, this is 2 meters, FBC times 2 meters equals 0. So FBC is 1,000 newtons, and it's in tension, right? CG was in tension, BC is in tension. Now I can go back and take the sum of the forces in the x direction. I have FBC acting in the positive x direction. The vertical, right? Here, I'll write it. FBC, FCG in the x direction, the x component of the force in member CG, and FFG is 0. I have 1,000 newtons plus 14 newtons times the cosine of 45, right? This is 45 degrees, so cosine 45 to get the horizontal component, plus FFG is 0. You've probably figured out by now that it's probably in compression. Get out your calculators. I get negative 2,000 newtons, so FFG is 2,000 newtons in compression. If you're wondering about on an exam, if you have this telling me that way is positive, keep the negative in there. It's really just easiest to, at the end of the day, go over here and say 1,000 newtons compression. So it's really like that. Okay. Now if I want to go look at the other side of the other section, well, let's see. This is FBC, which is 1,000 newtons. Is that right? Yeah. And it was acting in tension. FCG, 14 newtons, and then FFG, 1,000 newtons. If I do R dx, R dy, R ex, let's see, I can do the sum. See, there's two things. You can do the sum of the forces in the y direction. You can do the sum of the moments about D. You can do the sum of the moments about C. Then you don't have to deal with those components. Yep, that's what I did, right? So now we only have 3 unknowns instead of the original 6, so we can solve with equilibrium because we have 3 equilibrium equations. So let's start with the sum of the forces in the y direction. The only y direction forces that I have are the vertical components of the member force of FCG. Right? And then this reaction. So I have reaction at D in the y direction, and I have FCGY going down. So RDY is the vertical component of FCG, which is 14 newtons times, that's 45-degree angle, the cosine of 45 degrees. So it should be 1,000, right? Now, if I take the sum of the moments about C, that means I don't have to pay attention to FCG because it happens right there. I don't have to pay attention to FCY or FBC because it happens there. And I don't have to pay attention to RDX because it would have 0 moment arm. So I only, right, FBC, nope, that would be a 0 moment arm. FCG, that'd be a 0 moment arm. Let's see, FFG acts at 2 meters. It's acting in the negative, acting in the counterclockwise direction. So I have FFG times 2 meters. I have the reaction at E in the X direction, also acting at 2 meters. Reaction at D in the X direction doesn't matter because it would be a 0 moment arm. And then this distance is 2 meters. So it's also positive because counterclockwise is positive. And I just calculated this is equal to 1,000 newtons. Right, so I know that. Actually, I'll write that in a second. If I solve for REX, because I know FFG and I know RDY, REX is negative RDY minus FFG. I can get rid of that 2 meters, right? So it would be negative 1,000 newtons minus 1,000 newtons. Negative only means that I assumed it was acting to the right, and it is acting to the left. All right. Okay. I messed up, didn't I? Or did I? FFG is 2,000. I wrote it down wrong here. That means it's 2,000 here. And this should be 2,000. So this should be 3,000. (3,000 newtons acting to the left. So I know that this is now 3,000 newtons. Let's see, RDY still acting up. Was 1,000 newtons. Now my only unknown is my horizontal. Reaction at D. So I can take the sum of the forces in the X direction. I have FBC acting to the left. The horizontal component of FCG, FG acting to the right. The reaction at E in the X direction at 3,000 newtons. And RDX. The only one I don't know is RDX. So RDX equals REX plus FBC plus the horizontal component of FCG minus FFG. So let's see, RDX is 3,000 newtons. That's my REX. My FBC, which is 1,000 newtons. The horizontal component of FCG, which is 1414 newtons sine 45 degrees. Right? 45 degrees, so that's a sine for the horizontal component. And FFG, which is 2,000 newtons. So I get a reaction of 3,000 newtons. And I assumed it was acting to the right, and it is, so it's positive, so it is. Now, if you wanted to continue to solve this this truss by method of sections or method of joints, right? If we go back to the first one, maybe I could solve the A, or I could cut it. Well, that would actually be the same thing. I could, make strategic cuts. We will do an example later, live, but this was just one example of dividing it into two sections. Obviously, I still have several members that I don't know the forces in. So with that, I will thank you, right? And I guess also, actually, now that I say leaving, but you can also check global equilibrium, right? If my RDY, which you could probably guess, 1,000 newtons that way, this was 3,000 newtons that way, and REX was 3,000 newtons the other way. So some of the forces in the X are 0, some of the forces on the Y are 0. Always good to check equilibrium, do a little sanity check. Okay? So that is the method of sections, and that concludes what we will cover in trusses. Thank you.